good evening. Let's see if this all works. So far, so good. Good evening. Astronomy is mostly about testing our ideas of the world around us. How does physics work? But there's a part of astronomy that directly affects our lives on Earth. And that's not just, say, general relativity, which makes your GPS system work. But increasingly, we're beginning to be aware of the fact that the Sun actually sends things towards the Earth, and all of the other planets, but we happen to be on this one, that actually couples into our technology. And it isn't doing that increasingly. You've all vanished from my view now. My audience goes. But no, that's okay. You can make it slightly darker. I'll find my way. But we, as a society, are getting increasingly more sensitive to what the Sun sends out. And what I'll try to do in this talk is walk my way through this story a little bit to give you a feel of how the Sun affects this technology and what we're learning about it. Now, this is in part stimulated also by what NASA is doing. NASA, 10 years ago, started a program that it called a Living with the Star program. And the Solar Dynamics Observatory, for which we at the Star Labs built the main instruments, was the first of the main satellite missions to look at the Sun, at the origin of all of the space weather coming towards the Earth. So, let me take you through this story. And by the way, while I go through this story, I'm bound to slip into jargon. I'll try to define my terms. If I don't, just raise a hand or shout at me and ask me to clarify. I do not mind being interrupted for questions, so please feel free. If it fits in better at a later time, I'll answer it later, or I'll try to do my best to answer it immediately. So, with that said, when we think about the Sun, let's see if this actually works. Yes. We know, of course, that the light of the Sun is coming our way, but the Sun sends something else our way. This is called the solar wind. And the solar wind essentially is a stream of particles coming off the Sun. It could be a little darker, that might help. That moves by the Earth, largely by the Earth. And what you see here is an animation that basically tries to show you that that solar wind doesn't actually hit the Earth. It's largely bent around the Earth. And the reason it's bent around the Earth is that the Earth has a magnetic field. The solar wind has a magnetic field. The two don't like to mix very much. So one sets up a cavity, the shield of the Earth's magnetic field, and the solar wind largely blows around it. But it is in the interaction between the two that most of the it's okay. I'll let you run the lights. Okay? I can find it. It's in the interaction between those two magnetic fields that much of the space weather originates, that actually affects the largest, the most important infrastructure that we have here on Earth, namely the electrical power grid. So, I have to learn how to use this mouse. So, excuse me. There. We've basically, ever since humans have been on this planet, learned how to live with weather. But increasingly, we put more of our infrastructure in space. So as there are more satellites in space, they too are susceptible to space weather. And one of the phenomena associated with space weather is that phenomenon of the aurora. Now, I'll get there. The beginning of the story of understanding what the Sun was doing started essentially when Galileo Galilei in the early 1600s pointed a telescope at the Sun, a recent invention at the time, and he started making these drawings of sunspots day after day after day. And this is a series of his drawings of the sunspots. You can find them on the web. Which basically revealed to him two things. First of all, the Sun is rotating. Secondly, it is not immaculate. It actually had spots. Now, it took a while before people realized that those spots did something. It wasn't until 1859 that someone on Earth, for the very first time, noticed that these sunspots actually can power major explosions. Richard Carrington, a beer brewer in the outskirts of London, and Richard Hodgson, somewhere else in the periphery of London, were both looking at the Sun, at a region on the Sun, and they saw something that nobody had ever noticed before, a brightening on the solar surface. And I'll show you examples of that in just a moment. But not only did they notice that, they also noticed that a device measuring the Earth's magnetic field, a magnetometer placed in Kew Gardens, not too far from London, actually showed a swing at the time that just not too long after this flare was going off. And that's when the speculation started. Are these things related? How do you get something on the sun to influence the Earth's magnetic field? Well, that's a long story. It's a story that, of course, started already a long time ago. We knew about the aurora. We just didn't know what it was. If you go back into the mythology, this is something like the gods are having a big party. There's a big fox in the sky and it wags its tail. There's a school of herring off the coast reflecting light. All of these are potential explanations for the northern light. None of them was right. It wasn't until 1722 that the very first measurement of the variability of the Earth's magnetic field was made. Before then, people were using compasses and after to navigate. Nobody realized that you could go off by a degree or 2 or 3 while these geomagnetic storms were going on. And if you go off by 2 or 3 or 4 degrees for a long time, of course, you're going in the wrong direction if you do this for a long enough time. Then in 1741, someone that we know from the temperature scale, the Celsius scale, centigrade scale, Andreas Celsius, actually noted that, hey, this is interesting. We see these northern lights whenever there are geomagnetic storms going on. So the two must somehow be connected. It wasn't clear how they could be connected at the time. Then it wasn't until the mid-1800s when people started discovering that there was an 11-year cycle in how many sunspots there are on the sun. They come and go in numbers that go up and down roughly every 11 years. Not always the same, not repeating. But they also noticed that that magnetic field of the Earth variability was going up and down every 11 years. So the evidence for a linkage became stronger. But still, the process wasn't understood. 1859, I just told you, was the first time that someone saw an actual explosion going off on the sun. 1895, Christian Birkeland did an experiment with something called a terrella, a little Earth. He basically made a magnetized metal sphere and threw electrons at it with an electron gun, and he saw these little ring-like lightnings that looked a lot like aurorae. And he thought, that's interesting. I have a mechanism. But of course nobody knew about this phenomenon of the solar wind, and nobody knew that the sun was variable in its output and these big explosions going on. That's interesting. Pardon. Someday I will get to know this mouse. Just a quick question. One button. I've got the button now. It wasn't until just over a century ago that George Ellery Hale discovered that there was actually magnetism on the sun. Now when you say magnetism, there's a whole new way in which you can affect things. You don't have to do it with just a wind, you don't have to do it by light. Magnetic couplings are very efficient in the universe, but people still didn't understand how these explosions on the sun could have anything to do with what happened on the Earth until the 1970s, when from skylight observations from space, they saw for the very first time an actual, but not what we now know as a coronal mass ejection, an actual explosion leaving the sun at something like 1,000 to 2,000 miles a second, moving towards the Earth, and eventually enveloping the Earth and coupling into the Earth's magnetic field and creating this phenomenon called the aurora. Now the sun sends multiple things. I've given you a bit of a flavor already in our direction, into any direction of any of the planets. Of course it sends light. We know that it sends light because we're dependent on its light to keep us all warm here. I mentioned the solar wind, the wind that typically flows past the Earth at something like 200 to 300 miles a second. Yes, ma'am? Could you move that over a little bit so it doesn't cut off the left-hand words? Huh. Well, I don't know how to do that.
That won't happen. You'd have to change the screen resolution. You're in a different...
I can do that. I'm surprised it didn't do that automatically. So.
It's an older projector. It doesn't know the wider fields.
So what is this screen resolution? That
Yeah,
might,
try that.
that might work. Let's see what happens.
Do the opposite.
Okay.
There we go.
Perfect.
You won us over right there.
It sends, I have to be on this side, otherwise the mouse doesn't see what I'm doing. It sends light our way. I already mentioned it sends this magnetized wind our way, and the magnetized wind doesn't vary by too much. It varies by about a factor of 2 in speed, typically. It can go a little more than that, but typically it's about a factor of 2. What does vary a lot is the magnetic field that it carries. It changes in strength, and it changes in direction. And it turns out that the direction is very important because the direction determines how well it can couple into the Earth's magnetic field. The third thing that it sends our way is energetic particles. Now, it's still the same stuff that the sun is made of. It's mostly hydrogen and helium. It has some traces of heavier metals that you all are made of in it. But these are particles that are essentially moving at near light speed. And once you accelerate particles that light to that fast, they can do damage. They can do damage to satellites in space or to astronauts who happen to sit in space. And sometimes they actually make their way into the deep atmosphere. They don't harm us, but they are detectable by, say, neutron monitors that are placed in various places around the world. So the sun's light varies by a 0.1% or so over the years, hardly at all. In the X-rays, however, the entire sun can brighten by a factor of 1,000 or 10,000 in a matter of just minutes when a flare goes off. In other words, you should look at X-rays if you want to see a flare. X-rays don't get through the Earth's atmosphere, so you have to go to space. This is why we launched observatories into space to look at the sun. It has the nice advantage, it bypasses this thing that we call clouds for visible light, but it is essential if you want to see the most variable and the most dangerous part of the sun in X-rays or what we call the extreme ultraviolet, because it just does not come through the Earth's atmosphere. The phenomena that I'm going to be talking about somewhat, that we call space weather, are basically driven by forces that we're not familiar with. When we talk about magnetism, we don't use magnetism in our everyday life all that much. I mean, it's hiding in all your electronics, and it actually powers your traffic light changes if you drive your car on those little sensors. But we're not stuck to magnetic fields. We're not driven by magnetic fields. We don't have a real good feel for magnetic fields. So, and that's one of the difficulties that we have in astronomy, that once we go to these other conditions that we don't know here on Earth, we basically invent a new language to think of in terms of what's actually going on in these stars. So sometimes you get words that don't really make sense anymore. I may mention a few of them. But they have their historical counterparts. But they do couple into our technology. So these storms move the Earth's magnetic field. And when it moves the Earth's magnetic field, any conductor on the Earth's surface will sense those changes. Particularly long conductors. So pipelines, transatlantic phone cables, and electrical power grids, for example, will pick up these perturbations. And I'll show you some examples of what happens when that happens. Radiation, energetic particles, as I said, they fly through astronauts, and they can do damage to their biological systems. Fortunately, nobody's yet died or gotten really sick of this, because they tend to try to get out of the way. They hide inside, say, the space station whenever a major storm is predicted. Satellites can't move out of the way, so these particles fly through and their electronics gets upset. Sometimes so upset that they fail, sometimes temporarily upset. They have to reset, reboot. Communication systems might fail. Another thing that will happen is that the combination of the sun's light and those magnetic storms couple into the highest layers of the Earth's atmosphere that are somewhere between what we call our normal neutral atmosphere and this electrically charged atmosphere of high temperatures out in space. It's called the ionosphere. And some signals that we use in our everyday lives nowadays have to go through the ionosphere for them to be useful. That's the GPS system. So we need to know where a series, your phone, it needs to know where a series of satellites is in space. And it uses the time differences between signals coming to your phone to determine where you are relative to those satellites. What happens in these storms is that the ionosphere gets upset. The light takes a different path. And because it takes a slightly different path, the timing is slightly off. And suddenly your phone, or anybody else's navigation system, may think that you're several hundred feet, or up to, what is it, I'm thinking in yards, in meters here, up to 300-400 meters, so up to 500, 600, 700 feet, you could be off in your position suddenly. You haven't moved, but your phone, or say your aircraft, thinks that it has moved because that's the signal that is picking up. So for many of those societally important reasons, it's important that we understand space weather well enough that we can correct for the effects, or that we can forecast when they happen so that systems can use some other mechanism of communication and prevent those errors from affecting us in our daily lives. One example is the coupling into these power grids. This is an image of a computation of a power grid. It's northwestern Europe. And all the little black lines are the high voltage electrical power lines that are connecting all the stations that create power and all the main transformer stations that make it useful at the voltages that we use our electrical systems on. And normally, only the power that we generate goes through these power lines. But when the Earth's magnetic field is changing, it pushes power through those power lines. And those big red and blue dots that you see on the screen are a measure of how much power is being pushed in that shouldn't be there. So in this case, particularly Scandinavia was very susceptible. Scandinavia is a high latitude region. It's near the polar regions. It's near the auroral zone. It picks up these geomagnetic variability effectively. And it started pushing power through these transformers. And transformers do not like that. They're designed to not have direct current power flowing through them. They're designed to have you have a 60 hertz system here. In Europe, they have a 50 hertz system. There's regular oscillations running through. When you start pushing direct current through it, it heats up the transformer, it pushes electronics off where they'd like to be, and a major power failure in southern Sweden occurred just after this. The same, of course, happens in the US. This is a map of the US power grid, and people are beginning to wonder, well, how sensitive is the US power grid to that phenomenon of space weather? Until about 20 years ago, the answer would have typically been not very much at all, because in fact, that power grid looked completely different. 20 years ago, most cities had their generating power stations close to the city, so the power lines weren't all that long. And then, in the mid-90s, the Federal Energy Regulatory Committee started allowing long-distance purchases of power. Some of you probably remember some of the consequences of that, these rolling blackouts that happened in the late 90s and early 2000s, were part of that learning curve of where power was suddenly coming from. But it meant that the whole network was suddenly continent-wide rather than a few hundred miles wide. So it became a much bigger antenna, and it became much more sensitive to space weather. And yes, we think that it actually started picking up some of those things. This is an example of the type of measurements that we're trying to understand. And then I'll go back, I promise, to astronomy and looking at the sun. In the US, the United States Geological Survey operates a number of ground stations. Those are the little bubbles showing there. And what I'm going to show you now, as I start this movie, is you're going to see these bubbles vary. This is basically showing you how much the Earth's magnetic field changes in that location. The bigger the bubble, the more variable it is. And in some days, it varies a lot. And then there are these big black boxes. It turns out that the Department of Energy keeps track of whenever there's a major power perturbation. An outage, a big drop in voltage, a big shift in frequency, something that upsets the consumer or the electrical system that the consumer is using. Now the difficulty is, of course, there's always geomagnetic variability, and there's always something going on in the power grid. There's weather, there's ice storms and hurricanes and earthquakes and forest fires. and also space weather. So how do you disentangle these? Well, it took us quite a bit of thinking of how to do this. I'm not going to talk about this in much detail. Basically, what we found, I'll summarize it in words. What we found was that something like between 5 and 10% of all these power outages that we experience are driven by geomagnetic variability. And that between 5 and 10% of all the insurance claims for electrical and electronic systems are driven by geomagnetic variability. So they're driven by things that happen on the sun. Now you're going to say, that's not very much, 5 or 10% isn't all that much. The reason we think this is important is twofold. First of all, 5 or 10% of a big economy is still a lot of money. And it's avoidable in principle. But there are also stories that say, well, actually, what the sun has thrown our way could be much worse than what we've experienced. And the only way to learn about, well, the two ways to learn about a really bad solar storm hitting Earth. One is you're totally unprepared and this thing suddenly hits you and the power goes out for who knows how long. Or you look at the slightly less severe ones and try to learn from it so that you can protect your system or better forecast. And that's basically the moral of this story. We'd like to say we now know that there is an impact, so we can start understanding it so we can actually protect our infrastructure. Why is this so difficult? It's difficult because, I'll go back this one slide, because there's this force that we're not familiar with. On Earth, when we think about weather, basically we're talking about something that in physics is called hydrodynamics. It's the movement of water, but gas sort of in many ways behaves like water. It's a flow that moves around, and it's very difficult to do weather forecasts. But it has the familiar forces of nature in it. There's pressure and temperature, and then there's the phenomena that are basically associated with what water does in the atmosphere. Clouds, rain, things like that. And occasionally a little bit of electricity because there's thunderstorms. Cloudscapes on the sun look completely different. That is a cloudscape on the sun. Now, can you dim the light? Because it'd be nice to just show this in full glory. This is a really strange cloudscape. What you're seeing is strands of material moving up and down. It doesn't move like a regular cloud. There's no billowing. It goes just up and down, and it seems to just outline these little strands there. Well, that's because when material gets as hot as it is on the sun, and it senses a magnetic field, it can no longer just move independently of the magnetic field. All it can do is move along the magnetic field, up and down. It can't. And if it moves sideways, it's because the field is moving sideways. And this is a force we're not all that familiar with. So it took a lot of thinking and a lot of computer power to think our way through what magnetic fields are actually doing. Now, these are stunning pictures in how sharp they are. If you think of this in terms of how big is that to scale on the Earth, you might think, well, you're not looking at all that much detail, because we're looking at things that are a few hundred miles in size still on the sun. So you can imagine there's a lot of stuff below the scale that we're actually imaging. The smallest thing we can possibly see on the sun with our current present-day instrumentation is sort of the size of the peninsula that you're on. And we are tiny little perturbations in that. So there's a lot of stuff still hiding underneath it. But it is an astonishing image, because if you look at the sun as a whole, that little blue box there is the entire field of view. And if you put this in terms of, well, how big is that resolution really? That's a dime at 10 miles distance. So a dime over in Oakland that you can see with this kind of telescope. So these are stunning telescopes. Sometimes, they call this the 1 in a million picture, you can get lucky and the Earth's atmosphere is just as still as it can be, and you can do this from the ground, provided you threw a few tens of millions of hours of computing time on it after the fact to restore the images to its perfect crispness. Or, as we do, you go to space and then you get it all the time. So that's what we do. We go to space. The sun in space looks very different. This is what I do for a living almost every day. We look at images of the sun taken in extreme ultraviolet. This is not the yellow-white sun that you're used to looking at from the ground. What you're looking at is extreme ultraviolet light, the stuff that doesn't come through the Earth's atmosphere. The sun's surface does not glow at that wavelength. So it's the dark sphere underneath is the sun that is very bright and visible and completely dark in the extreme ultraviolet. But above it, it actually has an atmosphere. It has an atmosphere that is a few million degrees in temperature. And what I'm showing you is in the shades of the color, we can finally, I always say, we can finally see the sun in color. What I mean by that is we have to assign an artificial color to this. Our eyes cannot see this light. So I chose a set of colors. And the blue is the coolest. It's about 1 million degrees. And the red is the hottest. It's 3, 4, 5 million degrees. And the sun rotates once every 27 days as seen from Earth. So you can see this is fairly sped up. You can see the sphere of the sun rotating. But there's no quiet day on the sun. It's continually evolving all over. Sometimes you see a big explosion go through there. And all of that is powered by the sun's magnetic field. Now, if I showed you only one of those colors, here's one, a little faster, you see even more variability. What we're after is what we cannot see. What we're after is the little white lines. The white lines are a rendering of what the magnetic field is, but we have to compute it. We can measure it at the surface, but we can't measure it in the atmosphere. So we have to compute what it does once it gets into the atmosphere. And magnetic fields, when they have electrical currents running through them, are really difficult to characterize. So those are very complex computations that we're trying to do. And all of that comes from underneath the surface that we can't see, period. So somewhere underneath the surface is something that we call a dynamo. Now, if I were honest, I'd say, when an astronomer says dynamo, they basically say, I don't know what that is, I'll call it dynamo. We know it takes a star like the sun with convective motions, overturning gas flows just under the surface. We know that the faster a star spins, the more active it is. So we know the basic ingredients of what makes a dynamo. But we cannot predict why the sun is as active as it is. We cannot predict what the sun's 11-year cycle is going to do a few years from now. So we don't really have a proper understanding of this dynamo process. But it works in every astrophysical body.
Question.
Yes?
On that previous slide, what do blue and red represent?
In this case, we can measure, I'm sorry, the lines that I'm showing you are the visualized magnetic lines of force. That's the magnetic field that you're seeing. The red and the blue are measurements of how fast the sun is rotating. We can use sound waves, helioseismology, to probe the internal structure of the sun and even measure how fast it's rotating. Some domains rotate a little faster, some rotate a little slower. And it's in that differential rotation that this field is being stretched. And by stretching it, you strengthen it. So we know the pieces, we just can't make the whole story. But a dynamo operates in almost every large astrophysical body. The dynamo works in the Earth too. Now, you may have been wondering, when I showed you the pictures of the field on the sun, it's very complex. There's all these lines going all over the place, whereas on Earth, it's really what we call a dynamo. It has a north pole and a south pole, and there isn't much else to it. So if I draw the lines of force for that, there's a north pole with field lines coming out and a south pole with field lines coming back in. So what's going on? Is the Earth not that complicated? Well, the Earth actually is that complicated. If this is a model computation, I can remove the Earth from this. They think that that's the structure of the field inside the Earth. So the only reason we're not seeing it is that because here at the surface, where we live, we're far from the dynamo region. All that mixed, confusing stuff is no longer visible. On the sun, we look at the very top of the dynamo. We see all that structure, and that makes life difficult. Now, on the sun, look at the bottom diagram. People have been counting the number of sunspots on the sun ever since, well, the telescope was invented, 1608, more or less. The real records don't go back as systematically as much as that. The Royal Greenwich Observatory has been looking at it ever since the mid-1870s. And they basically count how many sunspots are there in a given year. And you can see that this goes up and down very irregularly. That is the sun's dynamo doing what we don't understand. And the current cycle is disappointing. 10 years ago, I was looking at a sun that was very active, lots of explosions going on. Now, well, there's still explosions. Like today, there was a very nice explosion, but they're far less frequent. I like my explosions. Without explosions, it just sits there, and there's not much to study. So it throws fewer things at us, but it still throws flares at us. And the flares are powered by the sun's magnetic field. And the sun's magnetic field, the easiest, most easy recognizable signature of the sun's magnetism is the thing called a sunspot. The sunspot is a big collection of magnetic field, and it is so strong that it stops gas flowing. Everywhere else on the sun's surface, the gas is flowing. All these little islands that you see around it are basically material that's hot, bubbling to the surface, cooling down by radiating and falling back down in the little dark lanes. And it goes up and down all over the place. And every one of these little bubbles that you see is the size of Texas. The sun is a big object. There's 1 million Earths that would fit into the sun. This big area, the black area, what we call the sunspot, the field, the magnetic field is so strong it's basically stopped that overturning. Well, if you stop hot stuff coming to the top, it's going to cool off because it's going to radiate its heat away, and it's going to get cooler, but it can't get replenished from below like it does everywhere else. What happens? It's glowing because it's hot. So if you stop it from being really hot, it's going to go dark. It isn't black, it's just a lot darker than what is outside on the regular surface of the sun. And then these striations you see running away, the thing that we call the penumbra, is basically the field stands up straight in the middle, and inside you're looking at it largely inclined, and you suddenly see these linear cloudscapes that I showed you earlier. Now, in this movie, you saw what Richard Carrington saw, if you had paid attention. There was a big white light flare going off. Did anyone see the big white light flare? Some say yes. I'll show it to you a number of times, repeating. You see these white ribbons running away. Now this is accelerated. This is that entire process takes approximately 20 minutes in this particular case. And those phenomena running away is essentially what Richard Carrington saw. And he said, we've never seen this before. I'm looking at this. I need to find someone else who can confirm that I've seen this. So he ran off, couldn't find anybody, came back 5 minutes later, and most of the phenomenon had gone. Fortunately for him, Mr. Hodgson was looking tens of miles away at the same flare, and he could actually confirm it. That's how they got it into the Royal Notices, the notices of the Royal Astronomical Society, because otherwise people would have said, I don't buy that, but nobody's ever seen this before. That is the scale of the Earth relative to these sunspots. All things on the sun are big things. And by the way, that explosion is approximately 10 billion hydrogen bones going off at the same time. What saves us, of course, is that we're far from the sun. So the effect is diluted. And it's hard to imagine that 10 billion hydrogen bones going off at the same time look as dim as that. That's because the background sun is so incredibly bright. And that's also why we have to go to space to study this, because in X-rays, that background signal is gone, and we can really see in far more detail what's going on in the sun when these explosions go off. Another problem is that sunspots evolve all the time. You can see them form here. This is a series of observations that basically tracks a region across the sun as the sun rotates. So you can see magnetic field bubbles to the surface. It forms sunspots. They move around. As they move around, flares are being powered. And eventually they'll fade away again. These sunspots live for weeks, but that's all. They go. They disappear again. And that field on the surface is continually being replaced by new arches of magnetic field coming to the surface. They carry their own electrical currents. They power their own flares. And that's what makes predicting these things more than a few days ahead of time so difficult, because in many cases, the field that will explode hasn't even reached the surface. So it's very hard for us to predict what will happen a long time ahead of time. This is a little light curve. We have this annoying habit in astronomy of having really strange scales for things. You probably know about some of them. When we talk about the X-ray brightness of the sun, logically, that is A, B, C, and X. And every time you skip a letter, the sun becomes 10 times brighter. So this is a curve going over a period from February 10th to February 18th, sometime in 2011, when there was a big flare that went off. And you can see that there are lots of these little blips, but little blips that often reach easily a factor of 10. The whole sun brightens in X-rays by a factor of 10. That one there, the strongest one, is what we call an X-class flare. It makes the sun reach this X scale. Extra strong, I guess. I don't know why they call it that. The entire sun brightened because of this tiny little region flaring by a factor of 300. And that impacts our Earth's ionosphere, and that upsets our GPS systems and our trans-ionospheric communication systems. So anything that communicates with a satellite for data, for television, or for navigation purposes. Now, to study that, this is the thing that we launched to study that. The Solar Dynamics Observatory is about the size of a okay, that size. A VW bus, if that says anything. And the telescopes, the four that you see aligned at the top there, are the four telescopes that make the atmospheric imaging assembly that made all these nice EUV images. This continues to make all these nice extreme ultraviolet images of the sun. It has its own ground station in White Sands that continually receives the data. It's basically two television channels coming down continuously, feeding us astronomers data. And it shows that it records data with four 16-megapixel cameras and taking a picture every second, so there's a lot of data to look at. What does this do? It means we can look at the sun in all of its colors. We can look at it just the way you would if you were as unwise to look at the sun, but basically invisible light where you can see a sunspot. But we can tune it by looking at other colors. We can look at another color that is not the 6,000 degrees that the solar surface is, but 10 or 15,000 degrees. Or we can go to 50,000 degrees, or we can go to 1,000,000 degrees, or a few million degrees. We can basically dissect the entire atmosphere of the sun by looking at these different colors that we record with these telescopes. We can also measure the magnetic field. It doesn't show up very clearly, but the yellow, the blue and the red here are colors that if I take the picture away, we can measure the magnetic field at the surface, and then we throw a computer at it to compute what it should look like in the atmosphere. And then we try to understand what that does.
Good question. How do you measure the magnetic field at the surface?
If I'm precise, I should say we don't, because we're not really there. When light moves through a layer of this ionized material, it polarizes. What we measure is the polarization signal. We use basically a fancy Polaroid filter, and we combine the settings of the Polaroid filters to deduce what the magnetic field would have been for the light to look like that when it reaches us here on Earth. You just saw a number of these big explosions go off as we were talking about that. We have also what we call microscopes. We can look at, this is the full sun image. Sorry, it looks a lot nicer on my screen than here. But we've got this big full sun image, and we now have these other telescopes. In this case, this is the IRIS satellite that looks at much higher resolution at a much smaller field of view. And if you want to do that, you also have to look much faster. So it takes images at a cadence of fractions of a second to show us the origin, the beginning of these explosions. And then when they get big enough, we take over with the big full field of view. So we're basically nesting telescopes, observations, wavelengths, colors of the light to try and understand what the sun is doing. And the sun is like a cloud. I'm sure if you've flown through clouds, you realize that when you look at a cloud from a distance, it looks like it has a well-defined edge. But when you fly into it, like a fog bank, you realize that you're basically going for a while before vision fades. The sun near the surface works the same way. It's partially transparent. And we can look with these telescopes by tuning the color of the light that we look at. We can pick bands that are either much more transparent or much more opaque. And by doing that, we can tune where we look in the sun's atmosphere. So if you're a fan of line profiles, on the left is basically showing you where we're looking, but if you look at the right, I'll show it to you. We're tuning this wavelength, and as we tune the wavelength, the sun's appearance changes. When we're not in a color that the sun that the atmosphere is opaque, you look down at the surface. When you pick a wavelength, a color that is much more opaque, suddenly you see all these structures stand out on top of the solar surface. And this is looking at the edge, just to show you what that would look like. We can also look straight down on the sunspot region and do exactly the same experiment. So here we're looking straight down. There are actually sunspots sitting underneath here. I know this is an unfamiliar picture because I chose not to use a visible wavelength, but an ultraviolet wavelength. But here too, we can do this experiment from near the surface to higher up, and suddenly in the middle of the line you see all these arches that are basically outlining the magnetic field, and then we can go down to the surface. So we probe the entire atmosphere by just tuning our instruments around. And you can imagine that that's kind of tough, because you have to really understand how light behaves as it moves through the solar atmosphere before you can really measure that, make the observation into a number that we're after, a density, a temperature, a strength of the magnetic field, and a behavior of the magnetic field. We can do it. I always think it's neat to show you this particular thing because it shows you the consequences of the different opacity, transparency of the sun's atmosphere. In 1999, it happens a few times a century, in this case, Mercury moved across the sun. And what I'm showing you is a set of slices of those images where we basically follow Mercury as it moves across the sun. The bottom image is Mercury seen against the white light disk. And you can see that Mercury just skirts the edge of the sun when it reaches the North Pole. It just went right over the North Pole here. Just touches it right there. There, Mercury seems to be inside the edge of the sun. And at the top, it looks like it's well inside the edge of the sun. It's the same Mercury. It can't be in different places. What you're really seeing is that as you change the color, you're looking at the sun that has a different size because it has different opacities. The cloud is bigger or smaller depending on the wavelength that you're looking at. Kind of neat to see that illustrated by that. And someone mentioned comet. Sometimes we see comets move towards the sun. And sometimes someone like me can be so naive to think, maybe I'll see it when it gets really close to the sun. Now this is naive somewhat, because a comet is a really tiny thing compared to the sun. And it's not very bright at all. But it turns out in this case, we actually did see it. And I'm wondering if you can see it. You can see it beginning here, coming up. Let me point by my shadow, if I can find my shadow. Someone stole my shadow. You can see it come here now and shoot in that box in that direction. Now,
you turn off the lights.
By looking at this, we could actually measure. This was really close, low down. Not many comets do this. We only know of two that came close enough, and fortunately in the last century. Unfortunately, we caught both of them. So this is one where we measured it to be something like the size of a mid-scale aircraft carrier, which was entirely evaporated in a matter of 15 minutes because it was so close to the sun. It never made it to the end of the box. That's why there's no other side to the box. It just went in and vanished. Okay? So what? Well, that's... And really, if you look at it like this, you don't even see it. So it was really because we saw it fall in what are called coronagraphs against the night sky, we could compute where it was going to be at what time, and that's where we looked. And behold, we actually saw it. Otherwise, looking at this whole image, you'd never have seen it. It is still playing, and you can actually see it if you follow it. Then there was another one. I'm going to skip this for just a moment. Come on, we can do this. There was another one called C2011W3, and comets C2011W3, when they disappear, they become D. Guess what the D stands for? So this one vanished, but it did go all the way around the sun and did survive for a little bit, but then it disappeared. It was a bigger one and didn't come quite as close as the other one I was showing you, so it survived its closest approach for about half a day, but then it was gone. But we observed, our instrument is the thing that looks at the sun all the way in the center of that set of images. So you can see it in the coronagraphs coming in, and then we looked at it very close by. And when you look at it very close by, now I'm showing you something really odd. One of the ways in which we look at these images is say, I don't want to see what doesn't change. So what we do is basically subtract an image from the previous image. And all you'll see on this edge here is where things change. So you can see the edge of the sun, and you can see this comet coming. And then there are all these little markers flying on there. What we did was, we said, well, we don't really understand. Look, this is a region of the atmosphere that doesn't glow, so we can't see it normally. But this comet flying through it lit up at least a little bit of that atmosphere. And that comet evaporated ionized material that as soon as it sensed the magnetic field got stuck to the magnetic field. And you can see it. You can see these little striations in the tail. And you can see that it's deflecting in different directions. And the direction of the magnetic field determines in which direction the tail is going to flex. This is completely different from far away from the sun. And then we said, oh, we can try and do our best computer model of what we think the sun's magnetic field should look like. And we can put these little cross markers on it, and does it do the right thing? Mostly it did the right thing. So it was a very interesting confirmation of the fact that we could, in fact, use the computer models to compute what the sun's magnetic field would look like in an area that we had no other way of observing it than by this comet tail. This is the second one that we saw, and it's the second one that got this close in a century. Now we're waiting for another one to fall in from far, far in the solar system so that we can repeat that experiment. It was fortuitous. Now, so what do we do here? We're doing something about comparing observations with these computer models to learn where things lie, where the magnetic field of the sun sits. But magnetic fields by themselves don't explode. They're really, in a sense, like lightning. You have to put a strong electrical current on it for it to explode. And an electrical current makes its own magnetic field. So this is an interesting experiment where suddenly we say, where we're wrong, we learn something. Right? So on the left-hand side is an observation of the sun's corona with these computed field lines. And if you look at it in detail, you think, yeah, that actually matches pretty well most of the places. Not close to the surface because you're looking at the wrong kind of layer, but these large arches of field-outlined hot glowing gas, they match reasonably well. The one on the right, particularly on the right-hand side there, you can see that the structure of the atmosphere is pretty much at right angles with what we computed. Well, it turns out that those regions where that happens, where we're really wrong in our extrapolations, those are the regions that power these big explosions. And it's because they carry these big electrical currents that can basically short-circuit in the sun's atmosphere. And we can compute where that sits. We can compute that magnetic field, and then the red stuff is where the electrical current sits. So even though we cannot observe it directly, we can guess it, well, compute it with these computer models. Now, that's the beginning of the solar storms. But in order for them to create space weather around Earth, they have to go to Earth. And right now we have this wonderful constellation of observatories that are looking at the sun from different sides. We're looking at it here from Earth with ground-based observations, but also all of our satellites in near-Earth orbit, of course, are essentially looking at it from the Earth. But the stereo spacecraft, right now they're way behind the Sun, have been drifting away, looking at the Sun from two different sides, gradually moving away from the Earth. I don't know if you can see me, I'm waving my hands. Gradually moving away from the Earth in opposite directions. And this is one view, whereas a combination of telescopes that are looking at small, it's basically a telephoto lens and a wide-angle lens and a super wide-angle fisheye kind of lens, that they can actually track explosions that start on the Sun and make it all the way out to the little blue ball. I need to do this, right? The little blue ball there, to the Earth. So you can follow this explosion. It's going 100 million miles of empty space before it hits the Earth.
Is
So,
that other ball to the right of the moon?
no, this would be Venus in this case. The Earth the Earth is basically way off scale here. It's much
And
smaller.
what is that other thing?
That?
Yeah.
Venus.
Oh, Venus. Okay.
It's Venus. And somewhere here would be Mercury. Mercury's orbit, but Mercury wasn't at that place at the time. But they've basically pasted in the planets because they'd be much smaller than what you could see on this screen. They're very tiny things.
The stuff seems to be moving more or less in a straight line towards the Earth. Have you corrected for the magnetic field that make it curve? Or?
Okay. This particular one happened to be headed straight towards the Earth. Most of them, of course, don't head straight for the Earth. The Earth is a very tiny thing seen from the Sun, so most of them go in all sorts of directions and don't make it to the Earth. The one I'm showing you is one that actually caused a geomagnetic storm because it actually did hit the Earth. Second part of your question, what about the magnetic field? Well, that was what I was going to say. We don't know. We can't do that yet. We can now see the explosion propagate its gas, and we can actually use computers to predict when it gets to Earth, even if we didn't have this view, pretty well, 2 hours. But if we want to know what the strength of the magnetic field is going to be, what the space storm is going to be, we need to learn how to do the magnetic field. So one step to do that, again, is by using computer models. We can put the explosion into the computer and propagate it out from the Sun all the way to the Earth, and zoom in on the Earth, and zoom in on the Earth until you see its interaction. We can't do the magnetic fields yet.
In the previous picture, did it just happen that Venus was exactly in the direction of the Sun?
They were almost aligned, yes. So the Sun, the Earth, Venus, and the Sun were almost aligned. This happens a few times a year. And then, of course, when we have it come near to the Earth, our stuff gets really complicated. I don't understand that. It's not something I work on. But again, people put this in computer models and say, look, if the wind hits upstream here, the Earth's magnetic field, it flows around it, there's the Earth, it does something out there behind us. And because it does something at the beginning when it hits it, and behind us when it leaves, that's why when we see the northern lights or the southern lights, the aurora borealis and the aurora australis, it basically forms a nearly complete oval at these latitudes of somewhere around 50 or 60 degrees. So somewhere around the US-Canadian border, somewhere around Scandinavia, somewhere around the northern edge of Japan. And that's where the coupling into the Earth's magnetic field is strongest. There was, I think it was 1989, a big geomagnetic storm that actually did cause a power loss, a power outage in Quebec and surroundings, and left 6 million people for about 12 hours without electricity in the middle of the winter. They didn't appreciate that. It's one of the reasons why we're working our way through this problem.
Last question, are we looking down on one of the Earth's poles, or are we looking like along the ecliptic?
You're looking, well, that would be the same, I think, if I understand the question, but you're looking perpendicular to it. You're basically looking, the sun was over there, and the midday point is out here, and the midnight point is behind us. So the poles are up Like that. You're looking at it sideways still, the normal way of thinking about it. Oh, the other way, the other way. Yeah. Now, in order to understand that entire process, we need to understand all these complicated terms there. And that essentially keeps a whole lot of people busy that have their expertise in each one of these areas. It's like when you say ecology on Earth, you have to understand the biology and the climate and the landscapes and the weather patterns that might happen. The same is true for understanding space weather. Space weather is much like weather in this sense. When I ask you, what are you interested in weather, I don't know what you're going to answer if I don't know you. You might say big storms. You might say wind on the bay because I'm surfing. You might be interested in frost because you're protecting grapes. You might be interested in rainstorms because you're growing something. So there's lots of manifestations of weather. Same thing with space weather. It's not a single story, and it takes a whole lot of expertise. And we always show that picture the wrong way. Really what happens is that's the size of the entire sun and everything around it that you've been seeing so far. And that is the size of the Earth out to the lunar orbit. And the Earth is really tiny. So if we're just slightly wrong in our computer models, the forecast will change drastically. From a science perspective, I'd say we're pretty good. If the Earth had been moved a little bit, we would have had it right on. From a user perspective, the forecast is like, well, you just forecasted some rain and it didn't materialize. It moved, it came up half a state over. Well, some might say that's good, some might say you've got a lot of work to do. I think we have a lot of work to do. What happens? This magnetic field comes to the Earth and it interacts with the Earth's magnetic field. And really what happens is we're moving, you're moving a magnetic field past a conductor. The Earth is a conducting sphere. And when you do that, you've basically made, the word is back again, a dynamo. You've basically made what happens in a power generation plant where they move coils around magnetic fields. And you create electricity by doing that in an experiment. Now, if anything that we build that conducts onto that sphere, these currents run through the Earth all the time. I've showed you this bubblegram of the Earth's magnetic field varying. There's currents, electrical currents running through the Earth all the time. They don't bother us. But when they couple into these conductors we build, long high voltage power lines or long pipelines, then suddenly we become interested in it because it actually begins to affect us. And no, we're not the only planet that has space weather. This is a false color image set that was taken by the Hubble Space Telescope. And at the South Pole, you can see this green ring. That's space weather on another planet. So we can learn about space weather by looking at our own planet, and we can learn about it by looking at other planets. This is the downside. Okay, astronomers make really pretty pictures. But the one thing we cannot do, that a physicist can do, is tweak a knob. A physicist can do something in the lab and say, what if I changed this? What would happen? We can't do that. But we can look at other things. We can look at other planets. Or in fact, sometimes we can look at other stars. So one of the things I'd like to skip by that a little bit is, oh, I should tell you this though, before I get there. What's the worst that can happen? Well, bad things happen very rarely. It's like measuring earthquakes in San Francisco. If you didn't know there was a 1906 earthquake, you might think it doesn't get so bad most of the time. But we know that something bad can happen because we have these long records. On the sun, we've been measuring sunspots for just a few hundred years. Is that really the worst that the sun can do to us? So this is an attempt to visualize that in magical numbers. Sorry, these are the units that we work in. The biggest sunspots we've seen are somewhere that size. Flares on some other stars that we see, and now you have to read these numbers here, can basically get 10, 100, 1,000 times more intense. And that means that the spots that these stars have should be 10 or 100 or 1,000 times bigger. Now on stars other than the sun, we actually have measured that they have spots this big. Because what happens when a star with that size spot is rotating is it dims, it brightens, it dims, it brightens, because these big spots sit on their surface. So we can just measure that. The question is, can the sun ever do that? Have we been around long enough looking at the sun that we know it won't get worse than what we've seen in the past 50 years or so? Or could it get significantly worse? How do we learn about that? Can that happen? Well, we've got 100 and some years of pictures, as I said, of direct pictures of sunspots. That's the biggest sunspot we've been able to find on photographic records. Now, those are big. They're probably still not too much bigger than all sorts of the worst we've seen in the last 50 years. Can it get bigger? Well, we don't know. There's a record. A famous monk called John, who worked in the town of Worcester in England, made a drawing, and he said, these are spots that I see on the sun. Now, if I put that on the same scale, you wonder what's happened. There's clearly a dark spot there. Now, just to see a spot with the naked eye means it must be pretty big. And he probably saw it somewhere around sunrise or sunset, because otherwise it's too bright to see that thing anyway. But then he put that little structure around it. Is that a penumbra that he actually saw? And if he wanted to make a point that he saw something that nobody had ever seen before, and he certainly hadn't seen before, would he exaggerate the drawing just to make the point? Or is that the real size? In other words, we have no idea. The concept of what we now call refereed publications, that someone else looks at it and says, yeah, you gave a trustworthy, reliable representation of reality, just didn't exist. We have no way of knowing whether this is a real observation or an exaggerated drawing, but it wasn't a planet moving in front, because we know when the planets move in front of the sun, and that was not a day that a planet should have been in front of the sun. So it was something very unusual on the sun. But, as I said, when we can look at other planets for space weather, we can look at other stars for sunspots and for flares. The NASA Kepler mission, until its fine guidance system failed about 2 years ago, was looking at 150,000 stars at the same time, all the time. Woo. And about 50,000 of them were not so different from the sun. I mean, they weren't real counterparts of the sun, obviously. But they were sun-like in their mass, in their structure, in their temperature, and in their age. And if you look at 50,000 sun-like stars for 2 years, you've got a 100,000-year record. Much more than the 100-year record that we now have for the sun. And yes, they saw the top curve is in fact a light curve. Days are tick marks here, so 10 days, 20 days, 30 days. The undulation is the rotation of the star, showing these sunspots. Come to the front, go to the back. Come to the front, go to the back. The sun brightens and dims doing that. And on top of that, you see spikes. And those spikes are flares. But in order for that instrument to see them, they have to be tens or hundreds of times brighter than the brightest solar flare. So we know they can happen. Now the question is, how often? Well, and the one technical diagram that I'll show you is this one. We can, in fact, make a diagram that puts how many of these events do we see, mystical units. So 1 in 100,000 years, 1 in a year, 1 in 100,000 years, or 1 in 10 billion years. 10 billion events. I'm sorry, I'm going to all casts. 10 billion events per year, down to 1 event every 100,000 years. So this is an enormous range. And we can put all these solar observations here. And the largest solar flare we've ever seen would have been here, once every 50 years. But the Kepler data say, actually, if we look at stars like the sun, every 1,000 years it can get 10 times worse. Every 10,000 years it can get 10,000 times worse. So, to the best of our knowledge, by combining solar and stellar observations, it can get worse, but very rarely. And now that we have that kind of information... I'm sorry?
What kind of duration do we have on these very large events?
In the optical, they're typically between 30 minutes and 2 hours. In the extreme ultraviolet, the afterglow is much longer. It sometimes takes days for the glow to fade. So it really depends on the color that you're looking at. Kepler, it's a matter of half an hour to 2 hours.
What's the consequences on Earth?
And this is where we have to now hand over to other sectors of society. When the scientists say, we have this information that once every so many years, and I can tell you how many times a year this would happen. It's rare, but it can get worse. We would see a storm moving towards the Earth, this times more impactful. What do you do about this? This is a trade that at some point people made in the city of San Francisco. You write down a building code. Your structures must be able to withstand perturbations of this magnitude so often. And we know that a really bad earthquake, we just can't afford to build resisting structures too, because we don't know how to build them, or they'd be so expensive nobody could live here. At some point, someone makes a decision about this we must be able to withstand, that we just can't deal with. And we're getting close, and that's sort of the end of the story here, we're getting close to understanding the sun well enough and how things get from the sun to the Earth, and how the Earth's magnetic field responds to it, that we're getting to the point where we say, this becomes a political decision. What do you think you can recover from, and what do you think is unacceptable as a consequence? I'm going to stop at that point, I think. I'd just like to make this point, that when we look at the sun, space weather is there all the time. You might in the media find this emphasis on these superstorms that are going to come. Well, they can come, but we know they're rare. But we already know it doesn't take a superstorm to have a significant impact. So we're already suffering more in terms of cost from the impacts of space weather, far more than we're spending on understanding it. So far, that's the right investment ratio. How much further we want to go, ask me to come back at some point and we'll continue the story. Thank you. Now, none of that had to do with the book, Living with the Stars.
I know.
But that's an entirely different story. It isn't there yet. It will be in a couple of months. Yes, sir.
I have a real basic physics question related to this. I know that you get a magnetic field from a moving charge. So that suggests that this dynamo involves charges, within the sun. But how is it that in a gas that you can maintain, do they have any idea how you could maintain separation of charges that would cause this magnetic field, or?
Okay, well, the sun technically, we don't refer to it as a gas, it's a plasma, because it's so hot that the ions and the electrons have separated.
Sure.
Now, what we need is a current. We need to move one set relative to the other. We don't need to pull them apart. You just need to move one through the other. So you don't have to maintain a charge separation. And by all the experiments that we've done, either in computers or in labs, people have actually made big spheres of molten sodium and set them spinning and looked at what would happen to them. Electric fields build up by themselves spontaneously. The question is, how fast do they die out relative to how fast they grow? And it turns out that the bigger the system is, the easier it is to maintain something, because it takes so much longer to fade away. So when we say the solar interior is conducting, it conducts electricity, the reason it's so active relative to what we sense here on Earth is not because it's a superconductor. It's about as conducting as copper is at room temperature. But it's huge. So once you've got a current going, it just keeps going for more than the lifetime of the sun, it turns out.
Oh, okay.
So once you have it, all that the sun is doing to itself is rearranging it. It's just turning it and stretching it and twisting it, and in that confusion sometimes you get explosions, and the order that surfaces out of that is the regular, the quasi-regular 11-year heartbeat that runs in the background.
But there must be ohmic resistance.
Yes.
What keeps the current going? Where's the, as they say, the EMF?
spinning the star, essentially.
So it
It's
slows.
spinning the star. It takes energy from it. Yeah, it does that, in fact. The sun, when the sun was born, as we know it, as we reconstruct it by observing other stars, as soon as it's settled into what we call a mature star, really just sitting there fusing hydrogen into helium for the past 4.5 billion years, it must have started spinning about once every 12 hours.
What was that?
Once every 12 hours, half a day rotation period. And because the wind blows off, it's essentially taking rotational energy off the sun, so it's spinning ever slower. And by now it's spinning once every 25 days. If we wait another 4 billion years, it'll probably be once every 3 months or so. But it'll keep spinning, and every spinning star does what the sun does. The faster it spins, the more active it gets. The older it gets, the slower it gets, the more tired it is. So even though, as I said, we don't understand the dynamo, we don't understand the dynamo all that well, but it's exactly like people. How does a physician learn about aging? Not by looking at one person for a few weeks, right? He looks at a population. There's young people, there's old people, and then puts together a picture. Well, that must mean people age this way. We do the same in stars. We look at stars. They live for tens of billions of years. We don't sit around waiting for them to evolve. We just look at them at different ages and say, well, that must mean they must age this way, because otherwise we couldn't see them as we now see them in the sky. It's exactly the same as doctors looking at patients.
How do the astronauts protect themselves when there's an anticipated flare? Is there a protected area of the space station that's specially shielded, or?
Well, the space station itself, of course, is already a pretty thick structure. It's about 2-3 centimeters of aluminium. Sorry, that was the British word. Aluminum.
So just the thickness of the...
They basically go to the aft section of the space station, wherever aft is, whenever that is. When there's a forecast coming from the National Oceanographic and Atmospheric Administration, like the weather forecast, does a space weather forecast. Whenever that space weather forecast said there's likely to be one of these storms heading your way, astronauts go inside and hide.
Ah, okay. So there's a special area that's kind of resistant to the
that's
to the flare.
extra thick in terms of coverage. The airlock structure around it is so strong that that's the best protected part. Doesn't mean that's protected enough. I've sat at tables with astronauts that have actually flown to the moon. In 1972, there was one of these events. And they say, to the best of their knowledge, had they been outside the Earth's magnetic field en route to the moon, it probably would have killed them. Nobody could predict it at that time. We had no idea what was going on.
No.
It just happened to be that that Apollo flight probably was 14, 15, whatever it was in 1972, came a few months after that flare. So they didn't suffer from it. These flares, you have to realize, the ones that are really dangerous are rare. They don't happen all the time. So far we've been lucky. The struggle that NASA now has is sending astronauts to Mars.
Right.
Because sending astronauts to Mars is going to take 2 years out, 2 years there, 2 years back. In 6 years, you will be subjected to flares, and you're subjected to energy that comes out from the galaxy itself, what we call the galactic cosmic rays. Both of them are pretty darn dangerous. And the tricky bit is, you could say, let's build shielding. But unfortunately, these darn galactic cosmic rays have a really nasty trick up their sleeve. When they impact something like an aluminium shield, they shatter that shield in pieces, not breaking the shield, but they create so much of a cascade of energetic particles that it's in fact shielding it makes it worse. Well, you can't go without shield, and the shield makes it worse. This is kind of that's why so far we haven't figured out how one can survive to Mars. Some people have volunteered not surviving. I've always wondered if those are the people who want to go to Mars. But we can't now responsibly, we can't send people to Mars unless we solve that problem.
What, two questions actually. What is the time period that we now have advanced warning?
I'm sorry, what is the?
How much time do we now have advanced warning? And the other one was, when we sent the rovers and the other things to Mars, they were sufficiently shielded at that time?
Lots of answers there. Because space weather has these different incarnations, the warning time differs. The big coronal mass ejections move slowly at 1,000 miles a second. You basically have about 2 days warning. The energetic particles, the ones that are flying through this movie, all that snow is